Hi, I'm Denis from Kaspersky, and today we want to cover a silent break campaign, not only in a text form, but also in a video format, like we previously did with a Monty 3 malware. And let us cover this time all the stages of the campaign, which you could take a look in details in our text on a secure list. We would cover dropper model, actually two droppers compiled with the different compilators, launcher, shellcode, and a Trojan. So infection chain is before the last stages are quite large, I could say, but we could manage step by step. We could manage what could be the results. As you could imagine, for all these models, we wouldn't cover just everything together step by step, because our video would be huge in this case. So format would be a little bit different from Monty 3 one. I would just show you the already prepared IDB files in IDA, show you the main functionality of these models, how we actually analyze it and how we came to the conclusions. You could take a look in our secure list blog post. So let us start. The first model I want to cover here live is a dropper. Inside the dropper there is actually the first one compiled with a C++. Okay, C with the classes and std string. Actually, another one with a Go, we would came to it later. And let me show you the DLL main after the and only one entry point in this DLL. And in DLL main, which we came after the old initialization of runtime, it's a quite an understandable one in case of the process attach usage or case of this DLL. If the copy of legit Windows Verfault exe is already exists in a tasks directory, because the normal place it's a system32, right? It's not the tasks, it's just a copy of the legit file. We would see why they did it. If it exists, the malware, the dropper, would just delete all the file level indicators of compromise, if you want. So I see two files would be deleted, besides Verfault, also VerDLL deleted. Now you could imagine it's a DLL search order hijacking scheme, right? Once again. Also delete some value from the register from the auto-run branch. So understandable. And value Windows problem reporting, most probably in charge of the persistent of this malware. The main function for us after it is a dropper. Dropper function. What we could see here. Some resources are taken from this dropper binary. Okay, it's a dropper after all, and place it in strings, right? So some manipulation with a C++ container and with two resources with 500 and 300 as names put into the strings. What else? What else? Here I see just a copying of a legit Verfault. Makes sense. Okay. And creation of the VerDLL. If you would take a look at the libraries, dynamic load libraries, which Verfault is using, VerDLL would be for sure there. So search order hijacking. And let me show you here one feature of our precious decompiler. You see the block, and actually this block for you as a malware researcher may be not too important, right? It just the code tries to understand, are all the string inside the container, or does it have to take another link to some outside place where the content is stored. So what I propose you to do, I propose you just to close this block for you to easier analyze this part of the code. Take a look. With a numpad with minus, I have a laptop, so no numpad here. I would use the context menu, just collapsing And instead of a huge if, you see only collapsed one. It's a little bit easier. You could actually make the same here, because if you would analyze this code, it's just code related to the strings, nothing more. It's completely unrelated to the functionality of the malware. It wouldn't affect your analysis. So here as well, I would collapse it. And now we came to the real malicious functionality. The content taken from the resource dropped to the var.dll as a result, right, in the same tasks directory, and after it to the current version run in famous branch of the system registry with the name Windows Problem Reporting. Our copy of var.fault.exe would be placed, just the same as we saw in a deleter on a DLL main, right? We remember delete of this copy of var.fault. And then I see one more function which I named write events. Let us take a look at this write events function. Now we have copy of the legit executable. We have decrypted from the resource corresponding DLL with a specific name. But what is write events? In the write events, the code register event source. If you would Google this name, key management service, you would find it's existing event source for the Windows operating system. It's a real KMS, key management service, related to the licensing of the products. It's a normal event source with normal messages. What happens next? It's read already existing messages from it, right? But we are mostly interesting is the part of putting new messages. With our second data decrypted from the resources would be put over there to the event logs. Report event W. Here goes new messages. You could see them in the event logs, but by default you wouldn't see the binary part of it. You see, as one of the argument of report event, you would have the binary part of it. Also, what is interesting? Interesting here is the category ID. Category ID is in the ASCII form. It would be AB if you transmit it to the ASCII. In the hex, it's 4142. And the message ID would be start ID would be 0 at the start and auto increment of this value. So if on infected system the analyst would filter out category ID with the 4142 in hex in a KMS log source and IDs from the 1423 and above, it would be possible to gather all the code which dropper stored over there. And actually it's a shellcode which would be executed later. We would see it in the code of another model executed by the launcher. And after it, all is gracefully closed. KMS event log is closed. All is good here. Okay, write event logs. Let us just to feel we analyze all the function in this model. Once again, I would collapse with if instruction. The same collapsing actually you could do not only with if but with a while or switch or instruction. So feel free just to save space on your screen for the analysis. This one, I think, yep, it's quite secure to collapse this one. And I'm almost sure we wouldn't see anything crucial. Yes, all another one are just free of the memory also gracefully return after all the functionality is done. So I think here we described all the functionality of the launcher. So once again, it's a clearing of all the previous part of its work if the host are like reinfected, and dropping the one file, copy one file, drop one DLL, and put the shellcode into the event logs. Let us continue with the next models. And we already took a look at our first dropper. As I promised, it was a C with a, not even with the classes, C with the strings, right? But also in this dropper directory, we have a Go. What is inside? So one more IDA database. And in case of Go samples, it wouldn't be that easy to start to find the real start of this malicious code. As in the first case, we are actually taking a look at very prepared database. It's like we want to do it with time, show you many stages, but on a prepared base. How we achieve it? All the names, main start, you see OS exit, all the standard functions actually. This data is inside this Go sample. So it's just a matter of properly parsing the file with a script, and after it you would get the names from the standard models, from the main model of your Go samples. Let me show you, like this. So from the out of the box, in case of the newer Go compiler, this one is 1.18. In case of 1.16, 1.17, most probably IDA would just, with the flirt signatures, mark it for you, the name of the standard. But since the 1.18, the calling convention is changed. It becomes more registry-based, less stack-based. And I'm quite sure that the compiler would also in the next version would handle it, but so far we have to handle with an additional script. It's possible. And get all these names. So, and after it, we would need main, actually main is empty in this case. Main start is on our screen over there, main start, and it's quite huge I could say. So, a little bit of scripting, understanding the version of Go compiler, and we are good to analyze already marked code, named functions at least, in our decompiler. Okay, firstly, this dropper would check if the targeted machine, infected machine, is into domain using the syscall module. So from the net, IP, buffer, to understand is domain information existing here or not. So if it's not corporate, I suppose, without a mention of domain, maybe it's not in a corporate environment. Maybe they're interested only in machines which belongs to some domain, some corporate networks. If it's not so, it just gracefully exit, OS exit. Here is the interesting part. Resolve patch events, as I name it. Some of the names are given by the analyst. So if main start, it's a result of the parsing of the metadata by a script, with precious name is into domain, resolve patch event, it's some manual work to make so. Take a look. The obsession with event logs not limited with keeping the shellcode over there. They also try to be a little bit more silent and patch the function, NTDLL actually function, like notification register, like event write, etc. So all the functions which we saw in the first dropper on the level of the kernel 32 exported function, etc. actually, and other libraries here patched on the level of NTDLL. And patched with what? Here you could see the opcode and an argument for the patch. And if you would disassemble it, it's a pure and simple set arrayx to 0 and return. so it just do nothing. Please don't put any logs in a Windows event logs. Makes sense? Makes sense. So process of infection becomes a little stealthier after it. Okay, we did visit function. After it, getting the version, there checking if it's in case of it's a Windows 10, it would be some loading of additional libraries, very funny functions, decoding such a string, such an argument, decoding with a base64 algorithm 4 times. It really was funny. If you take a look inside this function, it's a cycle of debasing of the argument. And as a result, it's a kernel base, kernel 32, and TDLL. It's just a loading into the library. And after it, let us take once again resolve patch event. We already was there. And if you take a look, a lot of concatenation, a huge number of concatenation. Let us now try to understand what it's all about. If you would go to the very end of this huge function, actually all the value here, it's mostly the concatenating, nothing more. In the end have to be the usage of this concatenated string, right? Okay, the last one. After it, base64 decode, please. And yes, new cipher. Oh, someone would, after the base64 decoding, would decrypt it with a IS algorithm. IC crypto cipher, new CBC decryptor. You even know the mod IS CBC, right? And so, how we could actually handle it? Because all this concatenation are not pleasant. I could tell you all these blobs with the base64 encoded of IS encrypted data are not following, it's not sequential, not one by one. It's just placed in a different part of the data section. Actually, we manage it with some Python script inside IDA, so a little bit of one more scripting with with some Python I could manage. But result, it's here. It's decrypted next stage from this Go wrapper. So, and after it, you would see after all this decryption, OS open. So basically, it's a very functionality of all this huge function. It's quite a simple one. In the very beginning, it would be make some anti-detection tricks like patching of the TDLL functions, right? A huge amount of concatenation after with decryption and run. So we just after it could go to the next stage. And in this case, by the way, next stage would be the Cobalt Strike model. But which is more interesting, we wouldn't analyze standard packages like Slingshot or Cobalt Strike because it's just commercial tools. Regarding this wrapper, I think choosing of such a compilers like NIM, Rust, Go also trying to serve anti-detection purpose. So security companies has its own detections for the, okay, let us say more mature or more old compilers, right? And just manufacturers try to compile with something newer. But Go and Rust also, it's not that new, if you think about it. And try to avoid the detection just using some more strange compilers than C++ or C1. Okay, this branch is enough with the Go. So here, to sum up, we have some scripting to get the names, scripting to get the data for decrypt, and a little bit of analysis going inside this function to understand on which systems it would be run, so what is the functionality before the decryption. And as a next step, I propose you the launcher. The launcher would be this var DLL file. Remember our dropper, it's copy var fault, put var_dll and some amount of data into the logs. We would go now to our launcher, which is actually var_dll. Let us take a look. So here goes more entry points, which is quite understandable, right? It's pretend to be the legit DLL. So if you take a look, all these functions would just bridge to the normal in Windows System 32 legit place for the var_dll and nothing more. Just a small bridges. Here go once again in DLL main, so var_fold during the start because of the after run, right? We remember the system registry would, when a process attach, DLL process attach once again, would load this DLL into its memory space. And this code would be executed. Let us take a look step by step. Run from events logs, I call it. And you see here I already, like I showed before, I already collapse all the unneeded ifs related to the std string functionality, and we could concentrate on our main malicious functions. So here this function are quite familiar because we saw in a dropper how the code put the shellcode into the event logs, and here the same event category AB of 41, 42 to gather the code from it, right? Reading one after one, its category is like this, and after it, it would be returned from the function. So it's quite the same. Event log information type, so inside the KMS data source, it will be information type, category ID AB, and event ID starting from the 1423. All the same, so makes sense. Okay, and after it, if we really get something, if len is not 0, right, some code shellcode exists, I'm copying, allocation, and I see which I called to run, virtual protect, page execute read write, and run it. So just read and run. And this is our infection chain so far. After run legit copy, load malicious spoofed DLL, read from the event logs, run it. So I think now it's time to take a look at the shellcode itself, right? Shellcode inside the event logs, as you could imagine, wouldn't be the PE file, right? Now in our disassembler it looks nice, some entry point, map run, but take a look. It's just a flow of bytes from starting from 0, so you remember our launcher just takes the offset 0 from all the gathered data from the logs and run it. Here it's quite a typical shellcode tricks like get a current address, etc, etc. But after some manual work with it, you could get the decompilation all right, and I see some arguments for the function map run. Let us take a look what happens inside. Inside, as usual, with the shellcode, there is some resolver by a function address, Windows API function address by a hash code. Quite a usual technique for the shellcodes of dynamic resolution of Windows API function names. All the needed functions here are quite typical. Load library, get port address, it's a must, right? You see it everywhere in every shellcode. Virtual alloc, virtual protect as well, but also force get native system info and also flush instruction cache from the NTDLL. Okay, after it, you could apply all your structures like image DOS header, image NT header, or image export directory, etc., and see perfectly typical mapper and launcher of the PE file. What is a PE file? It's a first argument, actually, first argument of our map run function. I remember here goes the first argument. Let me take a look. I see one simple trick here besides MZ magic in this MZ file. Now we know it's a Windows portable executable, right? So for D5A is our, we are awaiting here on this place, but they just wipe a little bit, but really a little bit actually, just 2 bytes, because after it you could see at a plain sight all this PE header and PE rich and all the name of section, text, data, so it's still visible, but some automated systems of protection could maybe just be fooled with the wiping of the MZ header. Also one more simple trick to be a little bit more silent on the infected system. Okay, here goes all the parsing of our embedded portable executable in this shellcode, right? But I remember more arguments. What happens in the end, after the mapping? And after the mapping, I see the running of the entry point. Here we go. So as a result, after all this mapping into the memory, optional header address of entry point goes here, and just a call of entry point of our PE with the argument address of the same portable executable in memory, DLL process attached, so it's a true normal argument as on a second and third position. But it's not all I see. After the calling of entry point, something happens here. So once again, our infamous rotate right OD, right, existing even in a Metasploit, infamous algorithm of calculating the hash of the function name, it's also here. But what is the template, what is the right hash they're trying to find, and after it actually run? This is the result with the 2 arguments, right? So let me take a look. Hash 3 I have as an argument over there of our function. So hash 3 is actually taken from this hash 1 second argument, right? And it's a funny place, I could say, because of this hash, you know algorithm, you know the hash, but without any tables of such a hashes for all the words, because actually it's a name of exported functions, right? From the next stage. It's not a Windows API anymore. For the Windows API functions, you know all the hashes. And you could, like we see in our map.re, it's easier for you to resolve all these hashes. You could even Google it or use a simple script. But this one is custom, because you could export from your DLL any name. You could count all the hashes for Britannica, but please mind, it's a case sensitive, so you have to count the hash for the uppercase and lowercase part of the Britannica. You could, but maybe taking a look at the, we have a next stage, maybe we would have some hints over there regarding this hash. Actually, let me show one more script over there. And this simple Python script is the counting of the rotate right 13 hash. And actually, you could see the name, the load. So no Britannica, no huge dictionary. It's just why load? Because you would see in the next stage, we have this name is the only export name, and I just checked if the hash is right, and the hash is completely the same, E12, 4D, etc. So besides the entry point, the export would be also called. So what else do we want from this sample? This is it, only one function, and also I wonder, or maybe the last thing here, what is the argument of our load or exported function from the next stage? Arc1, Arc4. Let us take a look where we have it. So arg1, it's here. It's right after the hash, and arg4 transmitted to our load exported function is here. So one level up here and here, right? The address in the very end of the shellcode of the ASCII dave. Okay, we have some artifact in a natural language, I suppose, but quite short, and the 4. So arguments would be the dave and 4. Actually, I could tell you it's not used in the next stage, but it exists. Maybe this shellcode could be used not only for this mz file, okay, wiped mz file, with a little hidden magic in the start of it, but for another one where these arguments could be taken into consideration. In this case, it's unnecessary, but it exists. I think it's all regarding this model. Let me briefly remind you where inside the shellcode put it into the event logs, which launcher would take from it and run. So we take the PE file, we add mz header, and let's take a look at it inside our decompiler. I promised you exported function, right? Not to brute force all the Britannica in uppercase and lowercase. Here we go. Besides the DLL entry point, we have the load. Please keep in mind, this algorithm we have in a previous stage, which I showed you. It's taken into consideration the uppercase and lowercase first, and also count the hash for the trailing 0, the end of the ASCII string. So when I count the hashes, I also take it into consideration. And regarding this load, I promised you dave and a 4 wouldn't get any meaning here. You see, it's just a wait for the main thread, nothing more. It's just a running, the waiting for the thread. Okay, here goes the main logic. And DLL main, start address, some transmitted to another function, and actually here goes the main last stage. We wouldn't because you know from our previous session with the Monty Free, the analysis of the last stage could take hours, even if I could just describe you already analyzed last stage. If you could do it together for all the function, it would take ages. I would just to emphasize several things here. You remember, by the way, you could make this code shorter, right? Because once again, the string is here. So here goes the very important network IOC, indicator of compromise. It actually forming the IP address of the control server for the Trojan, which we successfully decrypt right in IDA algorithm. It's quite similar or quite easy here to be made right in the compiler, and you would get the IP of interest here in your last stage. So here goes all our infection chain. What I could add about the Trojans? Trojans could use two media. I suppose it made HTTP-based Trojan are made for the external communication with the control server, and based upon the named pipes, just for the working inside the local area network, like migration from host to host lateral movement. And command sets are also differs. One more profound command set contains a couple of dozens of commands, and simpler it's around 10 of the commands. So this is it about the last stage. Let us briefly sum up what we have here. So what we covered, got the droppers, two of them. The main one C with a std string, which we successfully make a more plain text in our decompiler, drops the var DLL, copy var fault, puts the shellcode into the Windows event logs. Go one, just in an interesting way, combine Cobalt Strike module and run it. We even have to script here with either Python a bit, right, to solve it. After it, launcher, the module which take all the shellcode from the event logs and run it. Shellcode itself is responsible for the jobs another stager put it into memory and run the code on entry point and on a load export. And we remember load would just wait for the main thread. I could, by the way, also cover one more interesting technique here, the patching of the launching module. For example, our var.dll would patch var fault entry point with the same XOR rags and return. Why? Because actually launcher don't want to Windows error handling actually executes, right? All what var.dll needs is to be mapped into the address space of the var fault, nothing more. That's why entry point is patched. And remember, DLL entry point executes before the corresponding exe entry point, right? So first of all, upload, put, map all the libraries, execute code on the entry point, only after is the process entry point itself, exe entry point itself. And the last but not the least, the Trojans. So here, only one of them, but be aware, besides this HTTP version, also named pipe version exists. If you want more details, I understand in a video format, in just 45 minutes, it's impossible to cover all these modules. What I want to do next time, show all the infection chain, one of the infection chain. They have several of them. In a text above, you could just read in more details about all this malware. So thanks for being with us. We also hope it's such additional to our public reports in a form of video format is also useful for you as reversers, and you could get some ideas out for it, and hope to see you in another reports and videos again. So goodbye.